Welcome to the monthly Astronomy Free Public Tours. This is a free event that's run on the first Thursday of every month and totally run by graduate student volunteers here at the Department of Astronomy and Astrophysics. And these tours are made possible by the generous support of the Damat Institute and also the Department of Astronomy and Astrophysics. So today, how things are going to proceed is that we're going to have a lecture, and it will be followed by a tour of our telescopes and planetarium shows for those of you who signed up for them. The meeting location and all the other information you need will be given to you after the talk, so please stick around to listen to that very important information. Okay, so our speaker today is Charles Zhu, who is a graduate student here at the University of Toronto in the Department of Astronomy and Astrophysics. He did his undergraduate degree at the University of British Columbia in Vancouver, and that's where he grew up. And now he studies merging white dwarfs with a professor here named Martin van Kerkhove. And so without further ado, here's Charles Zhu to present to you Bombs in Space.
Thank you very much, Alana. It's a pleasure to be here this evening, finally on this side of the aisle. Tonight, I'm going to be talking about something very near and dear to my heart, bombs in space. In particular, a certain kind of star called a white dwarf. It turns out that certain white dwarfs will explode, destroying themselves and producing a tremendous explosion called a Type 1a supernova, which can be seen clear across the universe. Before I begin, I'd like to wish everyone a happy Independence Day. Don't kill me. I was put up to this, but anyway. As well as a belated Happy Canada Day. I hope that some of you managed to get out and enjoy one of the many grand fireworks displays we had on July the 1st. Just another reminder that explosions are everywhere in our lives. So I was very tempted to try to equate the light show that we make with fireworks here on Earth with the celestial light show in the night sky. But it turns out that there's another man-made device that much closer approximates the explosions I'll be talking about. And that's a thermonuclear bomb, or a hydrogen bomb. Both of these use nuclear reactions for power. Now, if I say the word nuclear, that image is probably what comes to mind in many cases, or a nuclear power plant. But the most important nuclear device in our lives is undoubtedly the sun. The sun is a giant nuclear furnace. And these three pictures together may raise a couple of questions. Why is it that nuclear bombs explode, but the sun doesn't? And why is it that even though some stars like our sun don't explode, some white dwarfs do? Why is it that one is not like the others? And tonight, I'll be describing why. And while we're at it, we'll be talking about how nuclear fusion works and how to build a thermonuclear weapon. So, because of this, a number of people told me that I should really rename my talk to this. However, bombs in space doesn't get me in trouble with the government, so I'm going to stick to it. So, let's start with what an explosion is. I went online to search for a nice quantitative scientific explanation and turned out with Wikipedia. Wikipedia says an explosion is a rapid increase in volume and release of energy in an extreme manner. Extreme being a really scientific word, but we all sort of get a good feeling for what violence and nonviolence is in explosions. So, there's a couple of important consequences to this definition. The first is that it doesn't tell you what energy we're using here. In fact, it can be from many different sources. Here are some common chemical-based explosions, magnetic-based explosions, giant alien space laser explosions. But all of these things have a common undercurrent, the dynamics, or what happens in an explosion. So in all cases, we have energy being rapidly dumped into a material in some confined space. So a rapid energy release. This rapid energy release greatly increases the pressure of this material, much greater than the surrounding material. That gives you a tremendous outward going force which pushes everything aside as the material expands violently. So that's the rapid increase in volume. All explosions have this. And in this particular case, the alien space laser is heating the air inside the White House, which superheats the air inside the White House, which results in enormous overpressure, which blows up the whole White House. So if we want to talk about comparing different energies, different explosions, one of the most fundamental aspects of an explosion is the explosion energy. And the measurement that you might hear a lot on TV is something called a ton of TNT. This being the American ton, not just lots of TNT. And this may sound like a mass, actually, but in fact, it is defined as a unit of energy, which is reasonably similar to what you'd get if you went outside and took a ton of TNT and actually blew it up. But I've never done that, and I don't really know what that means. And so I'd like to give a few examples for using tons of TNT to describe everyday things. So humans eat food, and then we use the energy from that food to do whatever we do during the day. Turns out that the average family meal, this being somewhat a large version of, is equal to about 0.0007 tons of TNT. That's almost a kilogram of TNT. In fact, this box of cookies has about the same energy content if you digested it, which might seem a little bit weird at first because, you know, TNT blows up, cookies don't. And the reason for this is because the cookies are, when you digest cookies, the energy is released slowly. Whereas if you blew up TNT, the energies are released in a split second. That's the difference, and it's very important, and it's part of the definition that we saw a few slides back. As a side note, about a kilogram of TNT is also the energy used to create the biggest fireworks in the world. Most of that energy is used to lift the fireworks up because fireworks are made of like paper and wood, so it doesn't take much to blow them up. Going off to 1 ton of TNT, back to our previous unit of energy. If we reverse the equation that we had before, we get that 1 ton of TNT is about equal to 1,400 meals. That's about how much you eat in a year. It's also about how much energy you use if you were to drive an average family car from Toronto to New York. It's about 1,000 kilometers. So that's quite a bit of energy. But what does it look like if you blew something up with it? Has anyone watched Mythbusters before? Yeah, okay. So a lot of you may have seen this episode before. When I was watching the show religiously in the mid-2000s, they had an episode where they decided to test the myth that you can take dynamite, throw it into a cement mixer, and clean the inside of like cement that's dried up. It turns out that doesn't work. What a surprise. But in the end, they got kind of annoyed and said, what if we put as much explosive as we possibly can? So they threw in half a ton of high explosive into the cement mixer, and well, in case anyone is wondering, this is about the same amount of energy released when a cruise missile hits its target. So we're getting to like military-grade hardware here. But the most destructive devices ever created in human history are much, much more powerful than this. So I was wondering if anyone wants to hazard a guess as to how much more energy goes into this than 1 ton of TNT. 60 megatons. 100 megatons. 10 megatons. 20 to 1,000. So a huge range, but everyone's using that word megatons, which, of course, there we go, means 1 million tons. So all hydrogen bombs explode at an energy scale 1 million times greater than the Mythbusters explosion. And that's where the word megaton comes from, of course. This is also quite astonishing. The bomb that made that explosion weighs about a ton. How is it that you can take a ton of whatever material, explode it, and get over 1 million tons TNT worth of energy out? The answer is nuclear fusion. So here's our standard high school picture of the atom. And here are the electrons, and in the center, this glob of protons, positively charged, and neutrons, negatively charged, constitutes the nucleus. Whenever we talk about nuclear reactions, we're talking about just the nucleus. We don't care about the electrons going around it. Now, there's two basic reactions that we can think of. The first is called fusion. This is where you take two nuclei, and they come together, and they form a bigger nucleus. The second is called fission, and this is where you take a big nucleus, and you split it into pieces. It turns out that our nuclear bombs on Earth work using both principles. There are bombs that use uranium that work on fission, and the hydrogen bombs, or thermonuclear bombs I was talking about earlier, run on fusion. This is also the fundamental reaction inside stars, and this is what I'll be talking about for the rest of the evening. So let's say you wanted to build your own nuclear bomb for whatever reason. What's the reaction that you would use? Well, if you were building a fusion bomb, you would take hydrogen and use this reaction, where two hydrogen nuclei come together, fuse, and turn into a helium nucleus and a free neutron. You can draw it in colorful cartoon style, or you can write the slightly more scientific equation upstairs. This gives an enormous amount of energy, and it comes from an interesting source. If you were to take a really good scale and weigh the left side and then weigh the right side, you'd find that the mass of the two hydrogen nuclei is slightly greater than the mass of the helium nucleus plus the neutron. This change in mass, this deficit of mass was mass that got turned into energy. And we calculate the amount of energy generated using Einstein's most famous equation ever. E is equal to mc squared, which is also can be written as energy is equal to the mass times the square of the speed of light. The speed of light is a huge number, and the square root of the speed of light is a really huge number. And so even if you had a little change in mass, you can get an enormous amount of energy out. If you do all the calculations, you can find that if you took about a ton of hydrogen, and you fused it into helium, you would get tens of megatons of energy out, exactly as nuclear bombs do. So, fusion has been touted as that which would save us from climate change. It's a source of limitless free energy. Why haven't we done it yet? Why can we only do this in bombs? And why was it even so hard to make a bomb? Now, there's a very simple answer. Like charges repel. The hydrogen nuclei each contain a proton. Protons are positively charged, and positive charges don't like each other and will repel each other. This makes it so that if you had just a box of hydrogen under room temperature, the chances that two hydrogen nuclei can come together and get so close as to start fusion is nearly non-existent, which is why nuclear fusion doesn't happen on the tabletop. How do you get it to do that? There's two fundamental methods that you'll see again and again throughout the talk. The first is to increase the density by like a lot. This makes it so that there's so many neighbors around a single hydrogen nucleus that the number of close passes just has to be greater and greater. Eventually, you get a fusion reaction, and this is one way to one way to start fusion. Although it turns out it takes a lot of density to do that. The other way to do that is to increase the temperature. This increases the speed at which the hydrogen nuclei will come at each other. So it takes a lot more work to stop them from coming at each other and force them back out. And so the more temperature you can get, the faster these hydrogen nuclei go, and the harder it is to stop them from coming together and fusing. Temperature is a great way of getting nuclear fusion to start. So I've said that hydrogen bombs are also called thermonuclear bombs. And thermo means heat, so you might think that temperature is the fundamental part of what gets a nuclear bomb to explode. It turns out that the secret to creating a thermonuclear bomb is to use both density and temperature. This is called the Teller-Ulam device, and most thermonuclear weapons today are based off of it. You have an explosive trigger over here, and this is another bomb. It turns out the only bomb powerful enough to do all this stuff is a uranium-based fission bomb. Over here, you have your hydrogen fuel, and over here, you have your secret, top secret military stuff, a container that wraps around this whole thing. When the bomb explodes, this super secret military material manages to channel all of the strength of the explosion into compressing and heating the vial of hydrogen here, getting the nuclear reactions up so high that this entire vial fuses in an instant, creating the explosion.
Teller, and what was the second?
Teller Ulam. Stanislav Ulam, yeah. The most powerful nuclear explosion ever produced by humans was the Tsar Bomba, or that we know of at least, was the Tsar Bomba. And this was a Soviet bomb detonated in 1961 and produced 57 million tons of TNT, 57 megatons. This is, of course, 81 million meals, which is about the same amount that everyone eats in Canada in a day combined. So we've learned the secret to creating a thermonuclear weapon and how fusion works. Let's move on to our second question. The sun is a giant nuclear furnace. Why doesn't it explode? So the reaction that occurs at the center of the sun is very similar to the one that occurs in a thermonuclear bomb. 4 hydrogens become a helium plus some energy. There's 2 extra hydrogens here because the whole process is a little bit more complicated. Every single second, the sun, using fusion, generates 95 million billion tons of TNT energy. That is the equivalent of exploding 1 billion Tsar bombas at the center of the sun every single second. So that's like a lot of energy. Why doesn't the sun just explode? Anyone want to hazard an answer? Yes? Gravity. Does anyone else want to? Yes?
The amount of volume it's relatively large as well.
A big volume. Anyone else? Yes?
The core is exploding, and so it doesn't reach the outside.
Yes, so in combination with the volume idea, only the center of the sun is doing all this work. Yes, that's an important part of it. It's a continuous bomb, like a reactor, yeah. So all of this stuff are facets of the whole picture. And the whole picture is a little bit complicated and involves a little bit of balancing. So, as the gentleman over here said, the sun is really massive and has an enormous amount of gravity. This gravity wants to crush the sun into a point. What stops it from happening is the fact that the sun is hot. Hot gas creates pressure. That pressure pushes out and resists the crushing grip of gravity. The two, in fact, completely balance. So the sun never really expands much and never really contracts much. But as anyone who's ever worked with metal or watched people work with metal on television knows, if you heat something up enough, it starts to glow red hot. A hot gas also radiates, which is, great for us because otherwise we'd all be dead. But for the sun, it means a loss of energy because it's turning all that energy into light and radiating it away into space. What replenishes the sun's energy is nuclear fusion, which, as a number of people here pointed out, only occurs near the center of the sun where it is hot enough. That energy then travels outward very slowly until it reaches the surface. So everything's in balance. Gravity balances pressure, and the loss of energy from the light being emitted is equal to the amount of energy generated by nuclear fusion. Yeah?
Is it possible that for the energy release or the gravity to increase, and if so, would the sun explode or cool down?
We'll see something like that in a few minutes, actually. And also, if people could refrain from asking questions until the very end. That was a really interesting question because we're going to talk about that right in a few minutes. So this is kind of weird. I mean, it's a balancing act. That's always a problem because what happens if you start tipping things? It turns out that that's actually the most stable configuration of the sun. If you attempt to tip things in any way, it comes back to this previous position. And one of the ways it does this is through something called the solar thermostat, and that's important for our nuclear reactions. So let's say that I could magically go to the center of the sun and magically increase the rate of nuclear reactions. This is just like a thought experiment, so we'll just do it even though it's not really realistic. What happens is that a little bit of extra energy is generated. That increases the temperature and the pressure of the star. Because the gas is hotter, therefore it has more pressure. Now, there is a balance between pressure and gravity. But now that we have more pressure, that means that the sun needs to expand because the two forces are no longer in complete balance. Well, and here's the fun part. Expanding the sun decreases the temperature and the pressure because a gas that's expanding needs to cool. And because nuclear reactions are mediated by temperature, that drops your nuclear reactions as well. So any excess that you used to have is now gone. The sun has basically muffled what you were trying to do. And eventually, over a very long period of time, that little bit of extra energy gets radiated out as light, and the sun returns to its previous shape. Now you can actually do this in reverse by sort of reducing the nuclear reactions a little bit magically, and then the thing that you mentioned actually comes into play. Gravity becomes a bit stronger, so the sun actually shrinks a little bit, but that heats up everything, and so the reverse happens. You get an increase of nuclear reactions, and the sun bounces back out. So great, the sun won't explode, which is wonderful for us, and it will last for billions of years until it runs out of fuel. So the sun is currently fusing hydrogen into helium. Eventually, it'll run out of hydrogen in its core. It'll then get much hotter and start fusing helium into carbon. And then, once it's done that and it runs out of helium, it gets much hotter. But unfortunately, it isn't ever hot enough to start fusing carbon into other things. Instead, all of this extra heat generation just makes it so the sun balloons into a giant red thing and eventually expels all of its outer layers into space. And this is what something like that would look like. This is a picture of another star doing exactly that. This object is called a planetary nebula. On the outsides, we have all of that gas being ejected by the star. In the center, we have a little ball of carbon. That's the carbon that never ended up fusing into anything heavier. And once all of the gas blows away and that star finally dies, the only thing that will be left is that ball of carbon. That thing is called a white dwarf. This is an artist's rendition of a white dwarf. The artist decided to also include planets at random here. Not all white dwarfs have planets, or even many of them necessarily do. So yeah, sort of buyer beware there. But a white dwarf is the corpse of a star, like our sun, after it's died. There's no nuclear reactions that happen, and over the evolution of this object, it will never get hot enough and it will never get dense enough for nuclear reactions to ever occur. Instead, it simply cools as it's radiating all this light and slowly gets colder and colder. That may be a bit of a problem, because earlier I said that hot gas is needed to keep the sun from collapsing down into a point. So as the white dwarf cools, shouldn't it start to shrink? Well, it turns out no, because other forces come into play. Now, the fact that like charges repel isn't good enough for a white dwarf. That force is just not strong enough. But it turns out electrons have another trick up their sleeve, one that is defined by quantum mechanics. There's a quantum mechanical effect that says that electrons do not like occupying the same spot at the same time. Therefore, if you took a bunch of electrons and you attempted to crush them together, they wouldn't want to occupy that spot, so there's an enormous pressure that comes back out, much greater than even the like charges repel thing. This is what keeps the white dwarf from ever collapsing into anything smaller. So in fact, white dwarfs last forever. These balls of carbon that get colder and colder and eventually fade into nothingness. So that's why the sun doesn't explode as a nuclear bomb. It's a bit complicated, but good thing that it does. The things that it turns into, white dwarfs, also don't naturally explode. But at the beginning of the talk, I said that I love these things, and they do explode, so they obviously do. But more importantly, and more rationally, we have evidence of this. We've been seeing explosions in our night sky for thousands of years. And the more that we looked at these explosions, the more some of them looked like the explosions of white dwarfs. The ancient Chinese astronomers called these explosions Kexing, or guest stars. And these are stars that would be very bright, almost as bright as the planets, and would suddenly appear out of nowhere, and then fade away over the course of weeks. One famous one occurred in 1006 and was seen by Asian, Arabic, and European astronomers. They had no idea what this thing was, but they thought it was really important and they all wrote it down. Fast forward to 1572, when another very bright guest star appeared. This time it was seen, although he didn't discover it, it was seen by Tycho Brahe, the Danish astronomer. Being an astronomer, he decided that he was going to take some measurements of how far this thing was away from us. And what he found was that it was much further away than the sun, the moon, and the planets. And that was huge back then, because people then thought that beyond the solar system, the heavens were immutable. It was static and never changed for the rest of time. He showed that this wasn't true and changed everyone's thinking. But they still had absolutely no idea what these things were. They were just important. It took until the 20th century when somebody came up with a hypothesis that these things were explosions of stars. By then, people had a good idea they were probably explosions, but these guys came up with the fact that these were stars exploding. This is Walter Baade, and this is Fritz Zwicky. I love this photo, by the way. And they said that some guest stars are so-called supernovae, explosions of stars. Now, their idea is a little bit different than what we'll be talking about. What they thought was that a star would suddenly collapse down to a very small object called a neutron star, and then all of that energy of the collapse would go into the outer layers of the star, rip it apart, and create an enormous explosion. This actually does happen. We call it a core collapse supernova today, but it only happens to the most massive stars in our universe. And so back then, people still didn't have a really good idea of what was happening out there. So they said, okay, let's take as much data as we possibly can. Let's go and find all of these guest stars, all of these explosions that we think might be stars, and classify them. They classified them according to the elements they saw in the explosions, because that looked like a good idea at the time. One of these classifications is called Type 1a. And what that means, it turns out, is that there was no hydrogen or helium spotted in the explosion. This is really weird. Hydrogen and helium are the most common elements in the universe, and they're also what make up stars for the most part. So what in the world explodes and has no hydrogen and no helium? A white dwarf. And the first guys to come up with this were Fred Hoyle and William Fowler in 1960. They said that Type 1a supernovae are the thermonuclear explosions of white dwarfs. As I said earlier, nobody thought that you could actually do this in just a lone white dwarf, but they said everything seems to match. All of the explosion physics seems to match. So we're just going to put this hypothesis out there. And here's what they said. Let's ignore how you get the nuclear reactions to start. Let's say they've already started, so you artificially increase the rate of nuclear reactions. This is very similar to that thought experiment we did earlier. But it turns out that unlike stars, white dwarfs do something quite different. So we increase our nuclear reactions. That increases temperature, just like before. But pressure doesn't change. Now, why is that? Because most of the pressure support of a white dwarf comes from the fact that electrons don't like to be pushed into one spot at the same time, and not because things are moving around because it's high temperature. So if you heat up the center of a white dwarf, the pressure doesn't change, and the white dwarf stays in the same structure it has before, except it's just hotter. Well, that's a bit of a problem, because that increases your nuclear reaction rate. Hotter temperatures means more nuclear reactions. which means more temperature, which means more nuclear reactions, which means more temperature, so on, until the nuclear reaction rate becomes so fast as to go through this entire star in only a few seconds. And that is a type 1a supernova. All of the calculations we've made since then, and many of the observations that we made in real life, support Foyle and Howler's hypothesis. Nowadays, when we want to see what happens when you explode a white dwarf, we run computer simulations on these giant banks of computers, and then we make pretty movies to impress our friends. This is one made by a group in Germany. And what it shows is they lit an explosion at the center of this white dwarf, and you'll see it as it propagates outward, enveloping the entire white dwarf and destroying it. This movie runs more slowly than real life. In fact, this takes less than 4 seconds to do, as you'll see in the time down here. Also, the white dwarf is not actually spinning, it's the camera that's spinning. So something is happening at the very center and becomes a lot more evident about now. And now you have this super hot ball of stuff that gets blown away about now. And blown away is a good description because, in fact, the speeds at which these things are ejected from the explosion is about 10% the speed of light. This is a ridiculously powerful explosion. This is also a fusion-based explosion. The power source is the nuclear fusion. So in fact, carbon is being fused into heavier and heavier elements, starting with things like silicon and magnesium and going all the way up to iron. This is the energy scale of a type 1a supernova. That is 24 million billion tons of TNT. That's 24 with 33 zeros at the end, and why scientists like to use scientific notation. And this is, I mean, it's unimaginable, this amount of energy, because there's nothing like it on Earth, and even the sun doesn't compare. In fact, this explosion, even though it takes place over a few seconds, releases so much energy that that super hot expanding ball of gas, that takes years to cool down. And this is why guest stars could be seen for weeks on end, and why our telescopes nowadays can track type 1a supernovae for more than a year. Now, I think the best way of describing the scale of this explosion is with this wonderful picture. I love this picture. Here is a type 1a supernova. Here is a galaxy. And the two of them are roughly the same distance. At the brightest the supernova ever gets, it emits the light of 4 billion suns. By comparison, the galaxy also emits a couple billion suns. So this single corpse of a star that came from a star that's not much more massive than our own sun, very briefly outshines an entire galaxy. Eventually, that explosion spreads that material that was fused out into interstellar space. Excuse me. And that stuff wanders around for a long time until it eventually finds its way into other objects. In many cases, other stars. In some cases, other planets. Type 1a supernovae are the most important source, basically the biggest source of iron in our universe. And so on Earth, all of the iron, from the steel in our ships and our bridges to the hemoglobin in our blood, comes from the most powerful nuclear bombs in the universe. So that's a great picture and all that, and all of the evidence seems to fit in. But there's one lingering problem. We neglected how to start these reactions. And this is where the trigger comes in. How do you get nuclear reactions to start in a white dwarf when they don't naturally do it themselves? Well, you know, if you can't do something yourself, get a friend to do it for you. It turns out the answer is another star. But exactly how that works is a question of current research. Now, we know that we're going to have to use either density or temperature. Those are our old adages for getting nuclear reactions to happen faster. But there are two leading hypotheses for exactly how you can have another star induce nuclear reactions inside the white dwarf. Here's the first. This itty bitty thing here, that's a white dwarf. This somewhat larger thing here is a star like our sun. And they have a very close relationship. So close that the gravity from the white dwarf, whoops, oh, gave away the punchline there. The gravity from the white dwarf begins to pull material away from the other star in a streamer. There we go. And this can actually occur over a very long period of time. What this effectively does is it piles mass on top of the white dwarf. So the white dwarf sees more and more stuff on top of it, it gets heavier and heavier, and its density has to increase more and more in order to generate enough pressure to hold itself together against collapse. Eventually the densities get high enough that the whole thing explodes because nuclear reactions start. This is the second hypothesis, the competing one. And this is a simulation that I did where we have two white dwarfs. This guy and this guy have about the same mass, and they have a very close relationship. They orbit each other like that. This interaction, turns out, is a lot more violent than sort of the gentle mixing that we had before. In this case, the two stars destroy each other in what's called a merger. And during the merger, you'll see the temperatures, indicated by color here, get really high, or in this case, really red. So the two stars become one, and we form this giant hot blob of material, which is really hot at the center. So hot that we might be able to trigger nuclear reactions. So here, we're using temperature to start our nuclear reactions, and we hope that that is what causes the explosion. So, who's right? Well, so far, we're not sure. Turns out that both of these pictures have their own problems. In the case of too dense, the reigning problem is that there doesn't look like there's enough of these systems out there. If we look through a telescope, we just can't find enough of them to explain the rate of type 1a supernovae. In the case of too hot, it might not work. Computer simulations have shown that it is tricky to get these white dwarfs to become hot enough during or after the merger in order to start nuclear reactions at the right spots. And so this is a topic of intense current research. I'm working on the too hot. Another graduate student here is actually working on the too dense. And a lot of people around the world are working on this and quite often bicker at each other about who's right. But that's science for you. And that is the hope, that we're progressing towards something, a definite answer, very, very rapidly. And it is my hope that within the next 10 years or so, we'll finally have a definitive answer. And we'll be able to tell you what the trigger is for these bombs in space. Thank you, everyone, for listening, and have a wonderful evening.
Time for a few questions if you have some for Charles.
Yes.
It's about how you said it, how might you think that you have two possibilities, and you're thinking this one is not too likely. It's possible that there's other life forms in the universe who might be raising the nuclear reactions inside white dwarfs. I mean, it's possible.
That is a brilliant idea, and I will tell you that I independently came up with the same one. There was sort of an in-joke that this debate has gotten so bad at certain points that I've joked that maybe the answer is that we just have aliens who like going to war with other aliens, and they use these things as explosions. That's a perfectly reasonable argument, except we have no evidence for it. So maybe. Yes.
I guess with the idea of mass being dumped on the star, would that actually create a hydrogen signature as well? Because most of the stars would have hydrogen on outer layers, regardless of age.
Yeah, absolutely. So what happens during that process, which is called accretion, is that this hydrogen-rich material comes onto the white dwarf. And in order to get it not to just sit there and stay as hydrogen, you need to actually start nuclear fusion at the surface. Except this nuclear fusion is a little bit more like the nuclear fusion in the sun. It's stable. And so it turns into helium, and then helium turns into carbon. And the hope is that you're just piling on more and more carbon, because as it's getting to you, it's turning into carbon. And that's actually kind of hard to do. And it's part of current research as well. Yes?
There is a rumor that our sun has a white dwarf somewhere in its proximity, and if that's the case, will it start bothering our sun sometime soon? That's a rumor.
And it would be news to me. The closest white dwarf I know of is Sirius B, but
But that would be the protagonist we needed to get our sun to explode.
well, possibly. Yeah, if there was a rogue white dwarf sitting there somewhere and in 5 billion years is close enough to us, maybe. There might actually be a collision between the two which would generate an explosion. But as far as we know, there's no nearby white dwarfs, because those that are pretty close to us are actually bright enough to be picked up by our surveys. So we'd be able to see one. Yes, in the back.
So you're saying the problem with the too dense one is you don't see enough of those systems. Does that mean that binary white dwarf systems are significantly more common?
So, by the way, this is sort of a complicated answer to your question. The answer is both yes and no. The problem is that a lot of these systems are really hard to find. And so, in the case of the too dense problem, what we see is, we think that what we're looking for is something that emits a lot in the ultraviolet, a bit basically bluer than blue. And we go out there, we count the systems, or we do something a little bit more complicated, and it turns out that there aren't enough of these. But maybe we're not finding them all. Maybe there's a couple that are hidden somehow, and that's what some people are working on. And in the case of how many binary white dwarfs there are, the problem there is that some binary white dwarfs are too far away to ever do anything to each other. We have to find the close ones, and we might have to find the close ones where the two guys are similar in mass. And that's not easy to do, and there are people working on that as well. Yes, over here. Yeah.
You said that white dwarfs never really die, but also that as they get colder, they fade away into nothingness. So what really happens to them?
They never really die in the sense that they never disappear or shrink into a black hole or anything else. They remain there, but they just get colder and colder and eventually become dimmer and dimmer and fade away from basically the realm of stars of any sort, because they're just giant, they're actually called black dwarfs at that point. They're basically just giant, really cold balls of carbon floating in space.
They crystallize.
And they crystallize. They turn into diamonds, sort of. Is there anyone in the back? Oh, yeah. Oh, excellent question. The question is, if the sun's hot gas pressure balances against gravity, why are there things like solar flares or solar prominences? Why does the sun eject stuff every once in a while? So the overall structure of the sun stays the same over long periods of time. So the sun as a whole will never throw out 10% of its material. But what does happen are these smaller, basically smaller instabilities near the surface of the sun. A combination of magnetic fields and some currents near the surface of the sun produce excesses of energies in certain places near the surface, and that is what generates a flow of material out of the sun, either in the form of little explosions like the solar flares or solar prominences, or more steady stream material like the solar wind. Yeah, over here. Yep.
What you said about the white dwarf couples, they're more than the white dwarf and star couples, but it's not that big for the two white dwarfs to
merge and explode, is it possible that just over the millions and millions of years, eventually the odds will have it that they blow up, and that's what causes the 1A supernovas?
I'm not sure I understood the question. So you're saying that just probability speaking that a single white dwarf would eventually explode?
No, two white dwarfs. They said it's not likely that they will explode, but there's more of them.
Uh-huh.
I'm saying the probability might say that eventually they'll explode.
So it isn't exactly obvious if there's actually more of the double white dwarfs that could lead to an explosion. There's a lot of double white dwarfs out there, but not all of them could lead to an explosion. So the probability is tricky, and there's a lot of people working on something called population synthesis, which is a complicated word meaning we do a lot of calculations to figure out what happens to pairs of stars and single stars. And they try to figure out these sorts of probabilities, and they disagree with each other a lot. So it's a complicated problem. How many more? Okay, over here.
What happens if the carbon fuses near the end of the life of the sun?
So what happens if in the evolution of the sun we have fusion of carbon? So there are stars out there, very massive stars, where you can actually fuse carbon into heavier elements even though there's still hydrogen on top of it, so it still looks like a star. These are the massive stars that eventually explode as core collapse supernovae. They turn into neutron stars. Yeah. Over here.
So I understood why white dwarfs couldn't get smaller, but I didn't really follow why, if they got hotter, why it couldn't expand.
So the two are actually very closely related, because both of them rely on the fact that a white dwarf is not held up by gas pressure. It's held up by the word called degeneracy pressure, which is that quantum mechanical effect I was talking about earlier, where if you take a bunch of electrons and you try to push them together, they don't want to stay in the same spot at once, so they push back. So if all of the pressure is generated by this form of pressure, this electron pressure, then if you start heating the star, it doesn't contribute much to the total pressure. And so the star doesn't actually expand and cool down, instead retains all of its heat.
But couldn't it? Why couldn't it expand? Because the electrons are pushing away from themselves. And then why couldn't it expand and stabilize the stars?
So basically the hot gas provides, so let's say that you start heating a white dwarf, right? So the the gas is now a little bit hotter, but most of the reason why it's being held up by anything is because of this electron pressure. Now, the hot gas contributes a little bit of the pressure, but very little. So if you heat it up more and more, it only expands a tiny amount. And then it basically makes it so that you can't cool off to the same degree as the sun would. Now, eventually you can heat it up so much that it does start expanding quite a bit because gas pressure becomes important, but by then you already explode, so it's not a big problem. Yeah? Absolutely. That is what most people actually think, that to some degree both of these things are happening, both of these possible channels to creating these explosions, but then people start arguing about which one's more important. So it doesn't actually end. To get this good picture, we have to do a lot of hard work and a lot of arguing. Yeah, one more? One more in the back then. Yeah, you in the blue shirt.
Has there been any data or simulations or even speculations as to how these phenomena would behave in close proximity to a large source of gravity, such as the center of a galaxy or a black hole?
Interesting question. Not that I know, not that I personally know of. But the fun fact is that may actually happen near the center of our galaxy. So yeah, that may be an interesting avenue of research. And is that it?
Yeah.
Okay.
All right, so that's it for questions. Let's thank Charles again.